So good morning, everybody. It is 10:30. We can start this new webinar of our free webinar series by EPMA. Welcome to this FM webinar, which is slightly different from the other webinars we have run in this series because it is on a special topic. It is on soft magnetic composites. We have two speakers here, Stefan Thiele from GKN and Flemming Boes Bendiksen from Syntax. Plus myself, I will have to give you a few words in a minute. Thank you for being here again. Please keep your microphone muted and maybe also your camera switched off until needed, so we spare some bandwidth. There will be also a poll that I will start in a minute because we want to understand what is the composition of this group, also because the meeting has also a target today here, trying to understand if we can start something new in the EPMA normal groups. So I will try to share immediately the Slido. You can find in the chat how to get to Slido if you want. Please go to the chat in this window and pick your pick the address of Slido so that you can join, because you will have to give your votes there. And I am sharing now the screen for the first poll that I would like you to take. So you can see also now probably on the screen how to join Slido. Again, slido.com, and please enter the code FM00. And so after doing that, you would be able to see the questions that are actually the ones that you see now also on the screen here in the meeting. You can join to Slido also with your smartphone if you want. So you're welcome to give your details, please, answering to this first question. We have 3 questions for this first poll. Yes, I see they're starting to come, and I'm already showing you real time what is happening. So maybe in the meantime, we can ask also Peter Clifton and Sebastian to say hello to everyone, as they are the chairs of the FM group. Maybe you have to mute.
Yeah, I am here. Peter Kelstein, welcome to everybody. We have within EPMA a working group called Euro Functional Materials that we initiated, I think it was 2 years ago, because we could see a large movement within the powder metallurgy associations that more and more moved away from the hot parts of the cars and more requested functionality of products. And when working with powder, we could see a big advantage. You can mix whatever you design the alloys you really want, and a lot of powder metallurgy processing routes can create alloys that are not possible to do with traditional technologies. So therefore, we agreed to design this functional material groups to focus on other kind of applications that just the standard mechanical parts that are mainly used today. And here SMC is we hope, or we expect, that it will be a hot runner in the future. But we also need more focus on it, and we need to understand a little more about why are people not using it? Why has there been a lot of hesitation? Because SMC has been on the market for, I would guess, 20 years or more. But the use of it is still as it's a novelty. So therefore, we hope that we, with this webinar, can bring some focus on SMC and also introduce to potential end users that there are other applications than just a motor. So we're very much looking forward to learn more today.
Okay, so we don't have many votes in the Slido, but half and half are manufacturing or wanting to manufacture or simply interested. I don't know if there are problems with connecting with Slido for the other half of the more than half of the people, but maybe we can switch to the second question now to go further in the webinar. So second poll, still you should see it in your Slido screen now. It's about how well you know SMCs. Please give us your status here. Yeah, coming. So it seems there's a good percentage of people who don't know SMCs. That's good. That's one of the targets of this meeting. Yeah, some more people compared to first question. Any more votes? Okay. Maybe we move on to the next question. Last question for this. Okay, another vote. We got it. We move it to the third question that ends this first leg of polls, and it is on the applications. What are the applications you're interested in? Let's see. Of course. Yeah, it would be interesting also to see what is other applications in this case. As you notice, we have multiple answers possible. So of course the sum is not 100, but it means that most voted is generally motors and generators. All right, any more? Okay. Right. I don't know if you want to comment a little, maybe a minute about these results, Peter and the speakers, and then we can start probably with the presentations.
Yeah, I thought it very interesting to see that several of the participants today have never heard of SMC before and are here just to learn. Mm-hmm. So that is very promising, and it also puts some pressure on the speakers because now you have to deliver a high-level presentation in order to secure that the newcomers in the SMC world, they leave the room today with a lot of new information in the head. So Thank you very much for participating and giving your replies to the Slido.
Okay, thanks. Yes, also on my side. And I think I will close the polls now and switch to my presentation because I'm the first one to speak today. I will try to keep the time spent at the minimum because we already spent some time. Sorry, this is the wrong one. I have to close this. We have spent already some time in the Slido thing, but I think it was interesting to understand what is the situation today in this meeting. And I will give you some details on what EPMA is doing for the FM sector. Peter already said something. Of course, I will go in some more detail of also other activities of EPMA. What we are, for the people who are not EPMA members, we are the Association for Powder Metallurgy here in Europe, and we already celebrated our 30th anniversary last year. We want to promote and develop and represent the PM community here in Europe, also at any level where it's needed. We are governed by the members, so the members decide what are the important activities in EPMA through the council and the board of our association. The technical part of the work is done mainly through the so-called sectoral groups, and these are actually seen as branches of the powder metallurgy tree, which is growing with roots in the powders, of course, and then branching into different technologies or materials. And the presence center was, of course, the first topic introduced in the association when it was started, but then other groups started. And the Eurofm is actually the youngest group in this family. And you can see all the groups there. What they do is they organize tour group meetings, but also seminars like the webinar we're in today, and we do surveys, and we publish publications for promotion of the technologies. Beside the sectoral groups, we also have what we call working groups, which are more transversal. And so there are two working groups at the moment. One is about environment, health, quality and safety. And it includes standards, chemical management and sustainability issues. And you can see the contacts in the association for that. One is me. And the other group I'm showing here is the EPMI, so European Powder Metallurgy Institutes, which is gathering all the research groups in Europe that are members of EPMA, and especially individuals who are involved in our activities, and they actually foster and manage some of the training activities in the association. Talking about Eurofm, as I said, this is the youngest group. Peter already mentioned that it was started in 2018 after a first seminar, which was successful. And you can see some of the activities being run in the group. In particular, the seminars. There have been 2 seminars, and we will have another seminar next month. Virtual, of course, but I will go in detail in a minute. And okay, publications, it's the first thing that it's a first edition that we are trying to put up at the moment, the Introduction to Functional Materials. It's under preparation. It will be available later for download on the EPMA website. And yes, we will also try to start some work on the statistics possibly in the future, but we don't know exactly how to do it because the functional materials group includes so many specific markets that it's difficult to put them all and have an homogeneous sample. but nevertheless, we'll try to do something. More on activities carried out in 2020. There was the Congress, and the Congress, which went virtual a few weeks ago, included 2 special interest seminars on functional materials, plus actually one which was called PIM of functional materials, so it was in the metal injection molding strand, so actually 3, and 2 technical sessions on FM functional materials. Of course, this webinar is another example, and then I want to invite you all, there's still time to register for the FM seminar, which is called Applications of Powder-Based Functional Materials. It's on the 26th, sorry, this is wrong, totally wrong, 17th, 18th of November. I'm really sorry. Go to the seminar webpage, please, and find all the correct details for it. It was originally planned for San Sebastian in Spain, but it will be virtual, so you can join also from home in case. And I already mentioned the booklet, Introduction to Functional Materials, which is being finalized, and you can see what could be the first page of this booklet. If you're familiar with the other booklets in this series, you know what we're talking about. In 2021, we plan another seminar. We already have a title and a date, Functional Materials for Energy on 1st and 2nd of June. Again, we will try to do it in San Sebastian, Spain, where CEIT is hosting us, and they accepted to move the seminar from this year to next year. So please join that later. There will be also a call for speakers for this seminar, so keep in touch. If you want to present something at the seminar, you're very welcome. Then we will have, hopefully in Lisbon this time, the European 2021 Congress, and of course we will organize seminars, technical sessions for functional materials as well, and possibly also on soft magnetic composites, of course. Normally we also have a sectorial group open meeting at the Congress. I didn't mention that. Also for this year we'll probably have it in December. So if you're an EPMA member, you're welcome to that. And under preparation, what I've already mentioned is that there is the wish to try to start something like a group for discussion, especially on SMCs here inside the Eurofm group. And we will also see if our webinars could include FM topics in next year. Right, so moving forward, I will show you what are all the events, and here finally the information about the FM seminar is correct, so you can see it here. These are all the events which have been moved from other times in the year in 2020 because of this frenzy and really crazy situation. We had to move them to the late part of the year, so it's a bit crowded now. There are many events, and I've highlighted the events linked to functional materials, but you're welcome to join any other event that you would like, of course. And save the dates also for next year. Here we have the FM seminar again, but also the other events that are already set. You can see that until a certain point in 2021, we're still thinking of having at least hybrid, if not only virtual meetings because of the COVID situation, which is not really improving too much these days. 1 day to lockdown here in France, actually. So just a few words more about the club projects. These are projects that are run inside our association, run by the members themselves. They just finance as companies. They put up a small consortium of 5, maybe 6 companies and finance a small research task, which is carried out in a few months or 1-2 years maybe. And we had already about 30 of these. They're very popular. Yeah, of course, it was not yet possible to run something in the FM group, but that would be nice to to improve and have the zero removed from the statistics here. If you want more information, go to the website or ask me. Projects, also we run projects in EPMA, and I mentioned here Supreme, especially because we have a special workshop in a few weeks. Please see it on our website. I also highlighted ESA project because there's something that we want to start. We're covering now. We're trying to monitor them and pass the information to the members every time there is an interesting call for projects in the European Space Agency, and I think that's also interesting especially for special materials like the functional materials. That's basically it. I don't know if you have questions. I'm ready to answer. Please keep ready to change again to Slido after the presentations when we will have new polls. And that's everything I had to say for today. Thank you. So I didn't mention, if you want to put questions, I would suggest you raise your hand or write them in the chat, please. But otherwise, if there are no questions, then maybe we can switch already to the first presentation. Oh, yeah. Yes, I will go to the first presentation. So I would call Stefan on the stage, and I would leave him the floor for his presentation on the fluid heating technology.
Yeah.
Thank you, Stefan.
Okay, thank you, Bruno. So maybe before starting, let me shortly introduce myself. I'm currently working with GKN Powder Metallurgy in the development of electric systems, electromagnetic systems especially, and I'm leading the R&D at GKN Powder Metallurgy for all these kind of products. Yeah, so I'm here in that position since 3.5 years now. I'm working with the powder metallurgy about 8 years almost. Okay, so maybe let's step into the presentation. Essentially, what I want to talk about today is first giving a short overview about GKN Powder Metallurgy, introducing the SMC topic, and as I've seen from the slide, some of you know SMC not that well, so I will spend some minutes on that. Then I will talk about the axial flux motors, especially as it's a key element for our key topic. So the case study fleet, which is a very interesting development made by GKN with some of our customers. Yeah, and finally I have a conclusion summing up what I have shown you. So let's start with the GKN Powder Metallurgy Group, just a brief overview. Many of you may know us already. One of the global leaders for powder metallurgy production, currently working in 3 fields mainly. So one is the Höganäs Corporation, which is part of GKN Powder Metallurgy Group, producing powders, various metal powders for our products. Then we have the GKN Sinter Metals division, where we produce the parts out of the powders. And finally, the newest element of our division is the GKN Additive Group, where we essentially handle all the different additive manufacturing technologies, starting from plastics over metals to special materials as well. Yeah, we are globally based almost everywhere in the big regions. We are present with our plants. I don't want to go into detail on that. And just give you another small overview about our size. So I think we are the biggest one with powder metallurgy products, working as said in over 30 manufacturing locations at the moment, having more than 6,000 people employed, and they are producing about 13 million parts each day. So quite a big production of parts coming out of our plants. So far for the company, and let's step into the technical topic of today's meeting of the webinar, so the SMC powder. And I would start with the introduction of soft magnetic composites. Within GKN, we have the brand name PM for EM for all electromagnetic products. So you will see that name very often. Also, our powder grades are all named like that. And yeah, what's the specific about soft magnetic composite? Essentially, it's an iron-based material which has an electric isolation layer around each powder particle. So that's a big difference to other competitive materials or conventional powder metallurgy products, that this electric insulation prohibits eddy currents in various applications. The process is similar to the conventional powder metallurgy. So we press the powder into the shapes of the parts, and finally we have a heat treatment, which is a little bit different because we have to keep the insulation intact, but it's also a belt furnace system in most of the cases where we can facilitate the experience we have from conventional powder metallurgy. Where was it used? The most common application is e-motors or generators. So there, the core or key competitor to our technology is the laminations, the metal sheets, which most of you will know are existing since more than 150 years in the market, and which is very well known, but which has a big drawback that they only can be designed in two-dimensional, at least if you want to build commercially effective motors. And with our powder metallurgy design freedom, we can build much more or more complex parts, having three-dimensional magnetic freedom, having three-dimensional design freedom for the parts. So most of the motors utilizing SMC look very different than conventionals. And yeah, that's the key aspect for SMC. Aside these three-dimensional isotropic material characteristics, it also has lower losses at high frequency. So in some applications, especially with high electromagnetic frequencies, it makes sense to replace laminations with SMC due to the lower losses characteristics. And Peter at the beginning already introduced it and told many people still don't know SMC well enough to build motors out of that. So there we as PM community working in convincing many of the customers, building prototypes, projects, and bringing the material more and more into the market and building confidence in this kind of materials. So one of the products which we use there is Axial flux motors. There SMC is very often used. But let's start with the basic principle of axial flux motors. So most of you will know conventional motors, which are also called radial flux motors, because there the magnetic flux in the air gap is going into a radial direction. So you either have the stator inside or outside, and the flux goes in the radial direction. Instead of that, compared to that, with the axial flux motor, we skip the magnetic flux by 90 degrees so that it's an axial magnetic field in the air gap, and therefore the design of the motors is quite different. And in many cases, it's very beneficial, especially looking on the rotor, which can be simply disc-shaped and which are very beneficial for different applications. Some will be shown on the next slides, so just wait for some seconds and I will show that to you as well. The big difference of axial flux motors is that with conventional laminations, it's quite complex to build them because you need, I call it all the time, 2.5 dimensional electromagnetic flux in the stator. So you have to go radially, you have to go axially, and with steel laminations, it's quite challenging to build up stators like that. So why should people and customers use axial flux motors? It's quite simple. There are a lot of more different benefits for different applications, but these are the most generic ones which fit to most of the products. On one hand, and that's especially for smaller motors is very important, is that with this disc-shaped rotor motor designs, you can integrate the axial flux motors very well into various space conditions, envelope conditions, and therefore you can build smaller motors, utilize your space more efficient, and at the end having more robust systems due to that. The power density is the next aspect for axial flux motors, especially if you want to build axially short motors. This can help a lot there as well. And you are very flexible in assembly by the axial design of all the motors. You just have axial assembly processes, which streamlines the manufacturing lines quite well. And in many cases, we already experienced that it's also have lower costs at the end in comparison to conventional radial flux motors. And yeah, we will see that in the case study later on as well in some details and shown at a real case study. So why do people use the SMC? First of all, it's a 2.5 dimensional shape of the stator poles which you need, or the stator elements. But on the other hand, SMC is a very well-proven material for serial technologies. So for example, at GKN, one of the products which we are producing, we have made more than 5 million parts. It's an example shown on the bottom right side, automotive water pumps. So it's a proven technology, well established in the market for some experts and people who know that material. And of course, the people choose the SMC also because of the design freedom. So you can build very simple, robust stators. You can make segmented stators, and you can add additional features, as you will see in this case study. Electromagnetic properties of SMC are getting better and better with each generation of powders. So we also can build up motors with high saturation levels. Currently about 1.7 Tesla is no problem to be established in an axial flux motor. And yeah, we, and especially the powder development guys, are strongly working on increasing the mechanical strength, and especially with current powder grades which are available, which are based on anorganic isolations, the mechanical strength is increased quite well to that what we had several years ago. So there was one of the common dangers known by customers is that SMC is too brittle, but that's a point where we can show our customers very often with the prototypes and the demonstrators that it's not the case anymore. I just want to show some examples that you get a feel that axial flux motors is nothing totally new and uncommon. There were several products already in the market in different applications, starting from automotive applications, industrial applications, and also in high performance e-motor systems. Axial flux motors already have their place in the market. And now let's go over to the case study. It's our fleet. That's the name of this kind of product, which I want to show you. And essentially, it's based on the axial flux motors. That's why I showed all the stuff before. But it's not only an axial flux motor, it's much more. So what was the idea? Very often customers coming to us having questions for new e-motors. And in some cases, we see, for example, in the case of pumps, that you have additional features like a heater, which is separated from the pump. We see it in urea systems. We see it in coffee machines, just to take out two examples where we are working on currently. And yeah, that's always separate systems. And we asked us, together with the customers, developed the questions, do we really need two separate systems which are linked very close to each other, or can we solve the problems by smart integration? And that's essentially what I want to show in this case study. So what did we do? We think about a heater in the two applications which I showcased. So for the exhaust gas systems, it's very important in the cold seasons, so in winter time, that the system starts operating fast. Due to environmental regulations, exhaust regulations, the urea system for exhaust gas cleaning must start up quite soon. And if the urea liquid is frozen in the tank, you have to heat it up. And therefore, the heater is much bigger than the pump itself. And yeah, that's just to the fact that we need to thaw the liquid before we can start pump. Similar, but on a different level of temperature, is the coffee machine, where you have a separated heater because you need to heat up a small amount of water quite fast. And there, this kind of heaters are plugged also in the piping systems around the pump, and it's just to heat the small water before you can brew the coffee. In both cases, we took our fleet design and adapted it to the customer needs. First, let's talk about the motor. We choose an axial flux motor, as already said, on one hand because it has better efficiency in the motor operations, and it's also enabling lower losses with the SMC design. And we showed a benchmark here, which is for the 50-watt pump system, where the conventional technology would be a brushless DC motor as drive for the same system. So it's a one-to-one comparison where we see that with the axial flux design, we can improve the efficiency, especially in this space environment which we had. Additionally, we have the function that we need to heat it. And how do we do that? Some of you will know that from your home or from traveling. This induction heating principle, very often used in the kitchen, to heat up the pans, the pots, and stuff like that. And we just thought, okay, it's a reliable and fast system to heat up anything, almost anything which is made of electrical conductive metal. And so with this technology and the adaptation to our motor, we find a very efficient way to locally heat up the fluid, whichever it is, if it's water, if it's urea or anything else. And we can adopt it to specific areas to heat up only that kind of fluid which we really need. And yeah, we experienced with our first trials that's very efficient, and that we can get very high heating power out of that, which can be 10 times the pump power of the e-motor, just with the same design of the motor and not doing too much different, but that will be shown on the next slide. Because why does it make sense to use this inducting heating principle, especially with AFM? Because in pump operation, you can use the motor with in a very efficient way, utilizing about 97% of the magnetic flux to build up the torque of the e-motor, which is even with conventional motors compared a good number. But on the other side, we always, or almost always, have an housing for the e-motor anyways. And yeah, we essentially can use this or the shaft for our heating operating. And therefore, with an intelligent design of all the elements and customizing the resistance, we can utilize them to produce the heat where we really need it. So, for example, in the housing, we can generate 95% of the heat just in the housing, and that's close to the liquid. And we guide the liquid along these areas where we have the heating. And furthermore, you would say, okay, now you have the heating function, but for sure you will need some more electronics. But essentially, with most of the electronics, we can control this inductive heating principle and have essentially no more costs there, or having at least less costs more. I just have an example and video for you that you see it, how it works in reality, because I think it's much better than having pictures. And I just want to show it to you. So that's our GKN fleet pump. In the inside, as said, it's an axial flux motor. On the outside, we have this heating housing, which we can adapt to the specific needs of the customers, as you see here, if you want to have higher areas. And yeah, essentially the function can be only pump mode. As said, efficiencies up to 80% are feasible with the small motors, and we can, at the same design, making a pure heating mode or an combined mode. And here you see a picture how fast we can heat up the heating or the housing of that motor going up very fast in the temperature. Once again, the video just showing the different operation modes. Okay, so far for the video. Okay, it looks quite interesting, I think, but let's talk a little bit about the benefits of this motor. Why do we do that, and why are the customer want to introduce that into their systems? First of all, as we replace the separate heater, the system can be smaller, and not only that, even the motor itself, the e-pump itself, can be smaller with our axial flux concept. And as we don't use additional elements for the heating function, the overall system significantly can be reduced. Furthermore, the design in this case study for the coffee machine, we can reduce the rate of about 50%. At the same time, we have increased the efficiency. We will see it in the next slide as well. And best, we need no additional elements, neither in the electronics nor in the pump. It's just utilizing what we have, and we can replace the heater without any additional efforts. We only heat the fluid where it's needed, especially for the urea system, which I showed at the beginning. That's quite important. If you need to heat up a large area of fluid, it takes longer, and as long as the media is frozen, you can't pump it and you can't clean your exhaust gases, and therefore it's very important to be able to start operation as fast as possible. Yeah, and finally, we replace the complete heating system included in our e-motor electronics, so the electric design is also significantly simplified. Bringing it back to the case study of the coffee machine, replacing the current systems and introducing our technology gave the customer the efficiency of a 40% smaller combined system. He also were able to reduce the number of pipes and cables in his system by 30%, and he has a 30% better overall efficiency. So meaning the combined heating and pumping function is 30% more efficient than the previous system. The electric design I just mentioned before was more robust, just one electronic board, which we have for both operations, and it doesn't add any cost to the system, even to the low-cost consumer product. We can keep the cost at the same level as the system before. Yeah. Finally, let's come to the conclusion of that. What I want mainly to highlight is the powder metallurgy, so especially SMC designs, give the customer and the designers a new kind of design freedom. In some cases, it's utilized by the customers, but very often we just replace the radial flux motor by an axial flux motor, having efficiency improvements, but we don't look on the integration of additional functions, which very often can be easily done with powder metallurgy design freedoms and especially material adaptations which are feasible with that. And therefore, we can much more integrate the systems utilizing the design freedoms which we have. And that's something which we as powder metallurgy companies, and especially at GKN, do, supporting our customers to think out of the box to utilize the benefits of our material best as possible. Yeah, and the case study of the fleet pump is one where we really can demonstrate it and showcase it very good, because you get the heating function for free from the e-motor, saving a lot of space, having a very fast heating principle, and still having a very efficient pumping, but all designed in a very small space. And this system also is feasible for dry running systems, for wet running systems, so you can use it in the different kind of pump concepts, regardless which one you prefer. And what we do very often is custom-made and tailor the applications to the specific customer's demand, meaning designing the housings, designing the fluid channels, adapting the resistivity, the resistance of the material, so that we can heat very locally and heat only whatever the customer needs. And finally, I want to thank you for your attention. And if you have further questions about this concept, about other concepts, you can always contact me. You see my email contact here. And for sure, if you're interested in detail, you can ask the questions after my presentation. Right now, introducing them by Slido so that we can address all your questions right now. Yeah, again, thank you for your attention, and yeah, you can ask questions.
Actually, I think we will move the questions and answers to the end of the other presentation. Stefan, we have collected already some questions, but maybe there will be more. I think the best thing is now to switch to Peter's presentation, to Fleming's presentation, and then we can have the question and answers at the end.
Okay, sure.
Yeah. So Fleming, the floor is yours.
Yes. Thank you very much. I'll try to share my desktop. Yes. First of all, thank you very much for this opportunity to speak to you at the EPMA. I come from Syntex, where we work with SMT materials, and we have. I have to speak today about linearizing loudspeakers using SMT. And this is a small agenda. First of all, I'll just introduce myself and Syntex, and then talk about the SMT materials. And I will show you how a normal loudspeaker with iron works, and the idea of using SMT in a loudspeaker. And I will show you the comparison with some simulations where I compare iron with SMT, and talk about the non-linearities in a speaker. And I'll show you at last that this has been ended up in a product by Dali, a Danish company, and then a conclusion. So my name is Flemming Bendiksen, and I have a master's in electrical engineering and an industrial PhD in motor design and control. I've worked for both Grundfos and Vestas and consultancy, and now since 2007 I have worked for Syntex, and I am now a senior magnetism specialist. I was also in the committee for UK Magnetic Society, and is still treasurer in the Danish Magnetic Society. Then a little bit about Syntex. Our core competences in Syntex is stainless steel parts for traditional sintered parts, like many of you know from the EPMA. We have metal injection molding, and we have magnetic systems and wear-resistant coatings. We have a revenue of 35 million euro a year, and we are about 150 employees at Syntex. We are part of the Grundfos group, which is much bigger, and it's a pump manufacturing concern. So now, Stefan has already introduced you a little bit to SMT materials. I've magnified one particle here, and you can see that it's quite small, and it's irregular in shape, and it has an inorganic insulation on top of each particle, and this is done to reduce the eddy currents running between the particles, so that this inorganic insulation will will make it more difficult for currents to run between individual particles. And we have to, when we look at the particle size, we have to balance also to maximize mechanical strength and to maximize magnetic saturation level, the density, if you will, when you do the compaction. And we have to, on the other hand, also still have the insulation between the particles. And in a way, also we're able to protect against corrosion to some extent, at least. So it's not comparable to normal iron in that respect. So from powder to finished components, you can see the 4 of the steps here. We have the powder, and then we do a compaction, typically between 4 and 8 tons per square centimeter. Sorry, and normally in the bigger end of this range. The heat treatment in combination with air, nitrogen, and steam, depending on materials and whatever you want to tailor your materials for. I'll get back to that in a minute. And we have the possibility of deburring and coating the parts. For prototypes, we usually prefer a cheap tool, but there's also a possibility of having making a bigger part and then machining out components. So the resistivity of SMC is 3-dimensional. We have the insulation compared to laminations, just like Stefan also told you. We have actually 3-dimensional properties of this material, and it's a very good thing, because then we can more freely design our parts. That's an example in the right here, where you can see lamination design and SMC design. And you can also look at, if you look at the resistivity in a lamination, you can see that it is really much more conductive than if you have a SMC material. Now, depending on what SMC materials you will have. Okay, and you can also say that mainly eddy currents in SMC runs internally in the particles. Actually, there are two ways of having eddy currents. One is eddy currents inside the particles, and the other one is having eddy currents to run in the bulk. So even though you have a quite high resistivity, you still, eddy currents are still able to run if you are not careful and you design your system correctly, and you can also do use different materials. So we can actually tailor SMC a little bit. The magnetic saturation level can be increased. Saturation level is set mainly by the compaction pressure and also the die temperature. The powder size, the coating layer, and the lubricants also have an influence on the saturation level. But typically, it is very high, and it's even comparable to laminations in some cases. The bulk eddy currents between the particles can be decreased by a fast and low temperature furnace, which preserves the coating and gives high resistivity. And we can also select from a range of different SMC materials and coatings. The eddy current loss in the particles is mainly set by the alloy and the size of the powder, of course. The hysteresis loss can be decreased by annealing. So a slow and a high temperature, you will fully relax the induced stress in the iron, which is induced by the compaction. So Mechanical strength can also be increased by compaction at elevated powder and die temperature, and we can also make a slow and high temperature, which will increase the bonding of the particles. But you can, as you can see, that it comes with a price of eddy currents. So you have to tailor and focus on what is really your need. Steam can also be added during heat treatment. Now, for you who like numbers, I made a table here of Syntex SMC types. It just briefly introducing what to look for. If you go to the strength here, you can see that we have 3 strong materials here, which are considerably more stronger than the other materials. So this is these 3 materials we call S in the end. If you want very low loss, you should go for the X down here materials. If you want the standard materials are on top here, and you can see that there's also difference between in all groups. You can see that you have M, B for bigger parts, where the resistivity is high, and you have even for high frequency, you have other alloys here. I just found out that I had to go at even higher frequency to be. You have to go to even higher frequency than 1000 Hertz to see the benefit, real benefit for H3 and H1. But they are there. Okay. So as I said, we have 3D unique magnetic properties and electric properties. We can do the design in a very compact solutions, efficient single operation production, where we just do one compression, and then we are more or less finished with the whole component. And in this case, as you can see here, compared again to laminations, for example, where you have to stack them and interlock and so on. There's a low waste. We usually have a few percent powder loss during production, and that it's a quite low price for the tool compared to lamination tool. We have low iron loss at high frequency compared to laminations, and 4 to 5 times higher saturation than ferrite cores, which you can also use for higher frequency applications typically, and we have even the same saturation level as for laminations, and we have then again saving on the components due to some of these factors. Now let's turn into the loudspeaker application. As you can see here, the loudspeaker consists of many components. This is an exploded view of a loudspeaker. That's something we call a G-yoke, which is the back of the loudspeaker. We have a magnet, typically a ferrite magnet, and we have sometimes aluminium shorting ring. I'll not go into details for this. We have a top plate, which is typically iron, and the G-yoke is also typically iron. We have a basket voice coil, which is the current carrying member for making the sound go into the coil as a voltage, and then convert it to a current, and then convert it to a force, which will then go to the membrane, the cone, making the sound. So the idea was, why not try to use SMC? But where should we use it, and why? Will it make any benefits? That was the idea. So a typical speaker works like this. We have a current running in the coil. This is cut outer section, I should say, and we have the magnetic field coming from the permanent magnet here, which generate a magnetic field that crosses an opening here where we have located the coil, and it makes a force which is proportional to the current and the B field. And we have the sections here you should look into is these three, the red one and the top blue and the bottom blue. We were thinking, what about changing all these regions with SMC? First of all, we make a static simulation here in three-dimensional, and we can see here the flux lines on the surface of material, and the flux density. That's the colors, and you can see the magnetization here, direction of the ferrite magnet. Actually, in this case, I think it's a Arduino magnet because it has a little bit of conductivity. We'll get back to that in a second. Now, we also made a static simulation in axial symmetry to see what actually happens if you take a cross-sectional area of again here you have the magnet here magnetizing, and the flux here crosses the air gap and get back to the magnet, and this is where the coil is located. So this is actually axis of symmetry is here at 0. In the left you can see iron solution, and in the right you can see SMC material. And the colors of course shows the magnetic flux density here. You can see that they look very much alike, so that's not a big difference at least in this case of using SMC compared to massive solid iron. So now this is a simulation where we ramp up the current, and you should be able to see that if we go to SMC, you can see that the current in the coil is generating a flux which is spreading very fast in the material. Both the SMC material is here, and here. And you can see the colors now show the current density in the parts, and you can it is to make it visible. This simulation, we have subtracted the DC field from the simulation. In the left, you can see the iron material, where you can see that the flux lines are not. They have a tendency to be captured a little bit. So they are not expanding so fast in the material. It's because of eddy currents. Please look at the scaling here also of the currents that runs. You can see that the scaling is 15 times higher for iron. So this means that you also have in the iron case you also have this currents running in your magnet, but there's virtually no currents running in SMC. Now this is more or less a comparable situation here, but now we have a sinusoidal current instead of a ramp. So you can see starting in the right again, you can see SMC it's quite fast it just penetrates the SMC material, and so it's quite fast to expand, and it makes no difference what current level you have, and there's no hysteresis. And if you look at the left simulation, you see at some points we have even shifted the sign of the current. So at some instances you have current running in one way, in one part of the ion and another way in another part of the ion. So in a way, the ion remembers. It actually stores the signal from the coil, and it makes a distortion. You could also look at this in other ways. It's a little more detailed now. If you know something about electrical systems, I put these in as a reference for you. So the sound signal is proportional to the voltage that comes from the amplifier, and the sound pressure that comes out of the speaker is proportional to the current in the speaker. So we have to come from the input is actually the voltage now, and the output is the current. So to make this linear, we have to have a system where the inductance is not changing. So even though we have an inductance, which is this is handleable, because if it's constant, then we'll have this term here as a constant, and we can handle this. This is just a first order equation. But if we have a changing inductance, we will have this term also, which makes a distortion. If you look at the ion case here, you can see that actually the inductance is changing as a function of frequency. And if you think about nice music, it actually plays with many different frequencies at a time. So you have the inductance is changing all the time. If you look at the SMC case, you can see that we have curves that are more or less constant, and you don't mind so much about these about permeability and position, but it's just to say that we have more time constant in inductance. Okay, so at Dali we worked a lot together with Dali, developing a new product for them in a very close collaboration. You can see here the black parts are actually SMC, and the gray parts where you come more far away from the inductance or of the coil. You can still use solid iron, and the backplate is also solid iron. This was an introductional model, and Dali calls these speakers Dali SMC driver. And to show you a little bit about the performance, you can they have measured the third order distortion. So this is sound measurement from Dali. You can see iron has a distortion that is higher than SMC materials, and you can even have a lower distortion by putting in some damping rings. I'll not comment on this just because this is more detailed about electronics and so on. But you can definitely see that there's a big difference in iron and SMC, and it made a very good product for Dali, and they actually turned in a patent application, which was actually in 2011. And they started in high-end speakers, which were a very expensive speaker. Epicon 8, it's still quite expensive. I think it's the same more or less today, 7,000 euro per speaker. So and you usually want stereo, so you have to multiply this by 2. But today you have a full product range of speakers from Dali with SMC. So you can buy a speaker now for only 200 euro. And you can, if you're interested, you can click on these links or write them up. So just to conclude here in the end, soft magnetic composites can be used in loudspeakers. linearizing the inductance as a function of frequency. And it reduces the distortion measurable and audible, and it's a huge success for Syntex and our customer Dali. Actually, Dali has won a ISA award for Epicon 8 as the best European high-end audio speaker in 2012 and 13. So I thank you for your attention and turn over the microphone to Bruno.
Thank you, Fleming, for your presentation. Just remind the people that we now have the question and answer time. So maybe I can ask Peter and Sebastian to moderate this part. We have some questions already for Stefan and also for Fleming. So we can start. And hopefully someone else will be willing to put some questions more by raising the hand. It's also easy to do it now. Peter, Sebastian, can you step in or okay, great, thanks.
Peter here. The first question in the meeting chat is from Sebastian. So Sebastian, maybe you should ask it yourself.
Yes. So welcome also from my side as co-chair of the function.
You're very low, Sebastian.
Yeah, it's very difficult to hear you.
Does it get better now?
Yes.
Okay, I just had my mic turned upside down. So, first of all, welcome everyone, all the participants of the seminar, also from my side, as I'm co-chairing the FM group with Peter, and glad that we could have so many attendants today. And my question was actually when I was seeing the process scheme of how the SMCs are produced at GKN. And then when you showed the induction heating, I was just wondering, like, could you also use the induction heating in the process to replace the furnace treatment to some extent? Because I mean, the faster heating and stuff. So perhaps you can comment on this idea and why it may be stupid, but so perhaps just out of curiosity.
Sure, I can comment on it. Unfortunately, due to IP, not too much, but yeah, there are people working on these ideas.
So it's not that stupid.
It's not stupid. It's something which maybe will not be in the market for most of the products due to costs in the next years. But there were some applications where it definitely makes sense to use inductive heating to tailor the SMC. Let's call it like that. And
Okay.
I said maybe in 2 or 5 years we will have more details about that, but currently it's development.
Okay. Thanks.
Welcome.
Next question, that was from you, Bruno, also to Stefan, the working temperature range for the SMC.
It's probably a bit connected to what Sebastian was asking, actually, because I was wondering what is the actual temperature range that could be covered. I suppose the resin that you add or the interface material has some stability issues at higher temperatures.
So in this case, it's not an issue of the temperature of the SMC. In most of the motors, the key elements, the critical elements are either the magnets or the insulation of the copper wires. So with our SMCs, we can go up to 300, 400 degrees without any problems, even with fast heating and cooling. So that's never the problem in the systems we had so far, that the SMC has thermal problems, even with fast or fast heating or low temperatures or high temperatures.
Thanks.
Yeah, thank you. Then next question is from Abdul Wahid. What are the design limitations of SMC-based actuators for heavy work like big power plants?
Okay, yeah, the actuators, I would like to understand more about actuators. I expect it's more or less e-motor driven systems. For big power plants and heavy work, you can utilize SMC as well. There were different strategies existing, at least at GKN, to build motors. And the biggest one currently is a 1 gigawatt machine where we are working on. So it's applicable from very small to also very big motors. But of course, you have to look into the specific application for, especially for the very big motors, to utilize the efficiency and the benefits of SMC best.
Yeah.
But if you have interest in something like that, please give me a note and we can discuss it in more detail.
Yeah, but typically when you go big, you need to segment.
Yes,
Due
sure.
to the lack of presses that are available.
Yeah, sure. It's
I also have a small note about it, because you should also be aware that SMC has a built-in air gap between the particles. So it does not matter for smaller machines and so on, but if you have bigger machines, actually you have an influence from having a lower relative permeability. So if you have bigger machines, the influence is becoming quite big. So put in another way, the SMC, the conductivity of SMC is having influence on bigger machines. At least that's what I found.
Yeah. Thank you. And then Bruno has a question for you, Flemming, about the potential to use this the other way around for microphones.
Exactly. Yeah.
Yes, that's also possible. Now there's I think that the microphone community is going another way, because they don't use so much systems like these speakers. You can use a system like that, very much look like the speaker here I showed you, but you can also use some other techniques, electric techniques to
Capacitor.
Yeah, which is I don't know what's it called. It's I think it's a capacitive way of working, and it's more used actually.
Yeah.
But of course, it is possible still to use SMC in speakers also.
Microphone. I think we should just step one question back, because Abdul Wahid, he raised his hand. So Abdul, if you have a follow-up on the question, please unmute and ask your question or your comments.
Thank you. I am Mohammed Abdul Wahid. Can you hear me?
Yes, we can.
Okay, thank you. So actually, I am working in a power plant, combined cycle power plant. This is, and there are many big valves, actuators, some kind of valves who are supplies water through the pipe diameter above 0.5 meters. Okay, so I want to know that what are the present achievable torque or for actuating SMC based servo motors, etc. Just curiosity. Thank you.
Yeah, the torque, we tailor our motors to the customer needs. So torque, it's always dependent on the customer. The range can be from a few millinewton meters, and for high performance motor, it can be several hundreds. So yeah, for the just mentioned 1 gigawatt, we are talking about almost 2,000 Newton meters in peak torque.
So if you use this material for making big motors, then this will also be efficient rather than the conventional ones, right?
Sorry, I didn't get the question. Could you repeat, please?
even if this is a bigger motor, the ultimate output will also be efficient rather than conventional ones, right?
Yes, you have to look into the specific details of the radial flux motor, but in many cases we can reach better efficiencies than the conventional ones. Yeah, and especially for big motors, the efficiency normally is much better than for smaller. So reaching above 90%, 94% is feasible with our motors as well. So.
Thank you. So this is really a big breakthrough. Thank you.
Yeah. And we have a last question, and it is from Fleming, so it must be for you, Stefan. Fleming asked about the demagnetization of the magnet from the heating and the high current. How does that look?
Yeah. Yep.
Yeah.
That's exactly is one of the key elements where you have to look for. Demagnetization of the magnets is one of the key aspects you have to look for. So that's a point where we have to customize and tailor the system to the customer needs, that we really get the heat into the fluid and that we don't get it too much into the magnets. Yeah, that's essentially the points. And in most of the cases, we can't. Well, we have to look for the right magnet class and grade to avoid that the system is overheating if you have a direct, especially wet running system.
Yeah, but I also noted you said one of the slides it said 10 times higher current than for motor operation. So I guess you need to have overcompensate also a little bit well, the thickness of the magnet.
No, that's a good point. In case of the heating function by the inductive heating, the magnet heating is quite neglected. So you have to custom tailor the housing and the resistance that the magnets are not influenced too much. Yeah, but that's feasible.
Yeah. Okay.
No more questions?
Sorry, I was muted. There are no more questions in the chat. So Bruno, I think we have a few more Slido.
We have some more Slido, some more games for the people. So I ask again, I will share again my window here. Yeah, I'll ask you again to go to Slido, and this time you have to add another code. It's FM01. I think the codes are very simple as we're talking about the FM webinar. And I hope you are getting there, because I'm starting the first poll. And this is the first question. So just coming from what you've heard today, maybe, what is your opinion on the possibility of substituting laminated sheets in magnetic applications with SMC? Vote, and then we will comment on this. Maybe I'll ask all of you in the, so Peter, Sebastian, Fleming, and Stefan especially, to comment on the results. They're actually, at the moment, very optimistic. Okay.
Yeah. Yeah, it seems that people have got the understanding on how it's technically feasible. But we have also experienced that if you compare it one-to-one and not compare the entire system, then it will be difficult in terms of price. But exactly as Stefan showed in his presentation, that if you optimize and design it properly, then you can save a lot on copper and on the housing and on the other parts of the product where you integrate. But I would also say that if you only compare, if you have a laminated motor and you want exactly the same design with SMC, then you don't use the technical advantage and you'll get a more expensive product.
Any more comments on the results now? Fleming and Stefan.
Yeah, I think Peter already mentioned it. Also from my experience, if you make a one-to-one comparison, even with very thin, expensive sheets, still SMC is not beneficial on the part price, but you have to look on the system costs. And there, with our SMC technology, we also can be very cost competitive, looking on the overall cost of an e-motor system and not only on the stator.
Yeah, the full assembly.
Yeah.
Right.
Yeah.
Shall we move to the question?
Yes.
So the next question is here. Where do you see the significant benefits of SMCs? Design, low losses at high frequency, noise, and so on, behavior, functional integration, or no benefit for the skepticals. But you're free to answer whatever you want. So results are coming in.
It looks very promising that there are. You have done a good job, Fleming and Stefan, because there are no people who have voted for no benefits. So you have been convincing.
Don't be shy.
Okay. Yeah. Yeah. So it's very good to see that so many are picking the design freedom, and as has been showed in both presentations, you can always ask for help if you have a design or if you have a product where you would like to use SMC or test the potential of SMC. There are many people who has used SMC and try different optimization designs. So just contact the speakers and ask. I'm sure they will be able to help with design suggestions.
Good. I always see 14 people voting. I wonder the others. You're still free to join even now. Okay. So just go to Slido and choose FM01 as a code. You can do it with your phone as well. Third question, and then we can talk a little bit. Are you confident about the mechanical properties of SMC compared to other electromagnetic materials? Maybe you have special applications and you feel not comfortable, but we have had some details about that. So we do have some negative answers here.
Yeah. Yeah, I think it's good. I think it's a good sign that we have honest people on board. And some of the recent, Stefan, you also mentioned something about it, that the first generations of SMC that was marketed was when temperature was elevated, became very mechanical weak. And SMC got the bad brand that it was very unstable mechanically. So therefore, a lot of people, they tried it, they made prototypes, and the prototypes broke down. And we still meet potential customers who are convinced that SMC is mechanically very weak. But I also remember the slide Fleming showed where there were free alloy systems where they had an S for strong, where the mechanical properties were, I think, about a factor of 10 higher than the original first generation alloys that were marketed. So therefore, I think we should be quite confident that there are systems that exist today that can fulfill the majority of the mechanical demands that you might have.
Is there a potential for improvement on these properties as well? Or do you think this is more or less the limit we can get with this kind of materials? You can answer.
Yeah, it's quite high today. We have a very strong colleague with very strong hands, and he's not able to break any of those parts.
So that's good enough.
Yeah, but
Okay.
if some of the no sayers here would like to share if they have any experience, please feel free to open your microphone or type your message in the meeting chat. I'd be very curious to learn about what are the reason for saying no.
And also maybe you could ask you, Stefan, what is your experience? You have already put some pumps on the market for some years now. Do you see any problems from a mechanical point of view on those?
Yeah. So maybe I will wait if some of the people
Sure.
from the audience answer and give us their comments. That would be very interesting for me as well, and then I can comment on our experiences.
Mm.
Yeah, feel free to step up and ask.
Yeah.
Oh well, maybe not.
No, it doesn't seem. So hopefully we have given a strong answer. But Stefan, please elaborate a little further from your side.
Yes. So essentially, as I said in my speech, mechanical strength for SMC is always a point where you have to care about. So I don't want to say we have solved all mechanical problems with SMC. It still is a different material than conventional steel laminations due to the material behavior, especially at vibrations, high frequencies, etc. There we are different. But the benefit is we have good materials now, which are mechanically strong and which we can predict very good. So the process reliability is very good. And if you have the SMC and you make the designs accordingly, you can handle them very good in almost every application. So we also have applications where SMC is directly mounted on the automotive motor block without any damping elements, and so even quite robust vibrations are feasible with SMC. So yeah, I would say take care for mechanics, but it's not an issue not to choose SMC in the motor. There was no problem which you can't overcome, at least from our experience at the moment.
Thank you.
Yeah.
So do we have another?
Yeah, another run of Slido. I will have to ask you to switch to another to another event again, code FM02. I think you made it already, so it should not be too difficult to do it. And I have the first question for you. Do you think the SMC can be beneficial when we look at sustainability and life cycle analysis? Yeah, answers are coming in. They all seem to be on the yes side. Yes. So it's overwhelming, I would say.
Yeah.
Can we comment on this? What are there advantages actually compared to the laminated sheets, or we're just talking about more or less the same level of environmental impact?
I could maybe comment. When I think about this and SMC, we have SMC compared to laminations. It's a more brittle material. So if you think about a motor made of SMC, you can actually crush it, and then you can take out the windings. It is more difficult to if you try to cross laminations. They will not. It's more let's say ductile. It's more. So at least for that perspective, if you want to reuse, for example, a whole motor, you can in traditional recycling plant, you cross everything and components come out, and they are more separate if you use SMC. I would expect.
It's easier to recycle and reuse.
Yeah. Designed for disassembly.
Yeah.
That's good. That's an advantage. Right. Next question, or do we have comments on this? Maybe go to the next question. Yeah, this is the important target. Maybe you want to comment, Peter.
Yes. We have talked about having an experience group, people working with SMC cross-organizational to a level where we can collaborate, we can test different new applications or new topologies of motors, because very often it can be difficult to be standalone and do things alone. But here it could be like a community where we can help each other building up new know-how in order to share it in the market afterwards.
Okay, votes are coming. Of course, everything is anonymous here, so you can vote freely. Don't worry. I don't see who is voting for yes and for no. We will probably ask you later in a survey if you want to join, and then that will be more formal, of course. For those who want to join, we will ask you the details.
Yeah,
but not now.
Yeah. But you slightly introduced the club projects that are within EPMA,
yeah.
And in other groups within EPMA, several companies go together and invest in an R&D activity, often performed at a university.
Yeah.
But instead of one company paying for everything, 4 or 5 group together and share the cost, but then also share the know-how that comes out of it.
Yeah, exactly. That could be one of the possible outcomes of more discussions and
yeah.
Just a place where where this could be more easily circulated and decided. Or
yeah.
So we have some base here to start with. Kid, any other discussion? We're already a bit late about, with our end time, so maybe if there are no other questions, I would move to the final one.
Yeah, let's do that.
Yeah, the final one is very easy. I just would like to have a feedback on this webinar. Just rate it 0 to 10, 1 to 10. Okay, 0 is not available. Thank you. And then you will all be free to go to lunch. And so maybe we should start thanking everyone for being here. And thanks to Peter and Sebastian who helped in the moderation of this meeting, of this webinar. But thanks especially to Stefan and Fleming for the presentations. I hope this could be also a good start for some collaborative work in the future in this field. And we all welcome you in all our next events, especially on functional materials, and but also all the other EPMA events. I am sure many of you already knew about the EPMA, so I'm probably smashing an open door for someone. Thank you. Thank you also for the appreciation of the webinar.
Yeah. Thank you very much, Bruno, and also thanks from our side to everybody who participated. Looking forward to hearing from you again. Feel free to write or call, both to the organizers and to the presenters.
Thank you.
Thank you, Fleming. Thank you,
Thanks,
Stefan.
everyone.
Thank you.
Sebastian.
Thank you.
Thank you.
Yeah. Goodbye.
Thanks,
Bye.
everyone.
Bye.
Bye-bye. Bye-bye.